We'll soon count something less trivial, but let me interject with a little remark here. Let n and n. Recall that Sn is the set of all permutations of the set n. And we call this a symmetric group, which is not a coincidence. This is a group in the sense of abstract algebra. In particular, if f and g are two permutations of n, then the composition is also a permutation of n. And if f is a permutation of n, then f inverse is a permutation of n. These are pretty useful facts, and usually they're used without much ado, so let me point them out now. As I said, if you've seen abstract algebra, this will not be surprising. It's just because composing bijections gives you a bijection, and the inverse of a bijection is also a bijection. Now, let's count something slightly less trivial. We're going to count permutation sigma with sigma 1 bigger than sigma 2. Not in itself a very useful thing to count, but it illustrates some things, some counting principles. So let n, at least 2, be an integer. How many permutations sigma in Sn, so permutations of 1, 2, and so on n, satisfy sigma 1 bigger sigma 2? Well, let's see. So we shall give two solutions. Each of them illustrates something different. First solution, let me give them names, or rather again, let me give them colors. A permutation sigma in Sn will be called green if sigma 1 is bigger than sigma 2, and red if it's smaller. These are the only two options, because the permutation has to be injective, so it cannot have an equal sign here. It's either bigger or smaller. So we need to count the green permutations. Since each permutation is either green or red, but not both, we have, by the sum rule, the number of all permutations in Sn equals the number of green permutations plus the number of red permutations. Now, I will not solve this for the number of green permutations, because counting the red ones is just as difficult as counting the green ones. That's not, we won't gain anything by solving this equation for one of them. However, I will do something else. I will claim that these two addends are equal. Whatever they are equal. Why? Again, it's reasonable to look for a bijection. So if you have a green permutation, how do you turn it into a red one, and vice versa? So we can encode a permutation sigma by its list of values. Sigma 1, sigma 2, and so on, sigma n. Usually people put brackets around it. However, I will use parentheses instead, because I've already used brackets for everything thinkable. That would be confusing. So thus, a permutation sigma is green if the first entry in this list is larger than the second, and it is red if the first entry is smaller than the second. So how do you make a red permutation green? You swap the first two entries. So hence we can make a green permutation, so a red permutation sigma green by swapping the first two entries, and vice versa. More formally, we have a map, let's call it F, from the set of green permutations sigma to the set of red permutations sigma, that sends each sigma to sigma with the first two values swapped. So when I mean interchanged, it's probably a slightly more precise word. So what does this really mean rigorously? How would you explain this? This means the permutation that takes the same values as sigma on the numbers one, so on all the numbers that are not 1 and 2, and take the values sigma 2 and sigma 1 at 1 and 2 respectively. Alternatively, we can define it as the permutation sigma composed with S1, where S1 is a permutation that swaps 1 and 2 while leaving all other values unchanged numbers. Because what happens when you compose sigma with S1? It means that 1 now gets sent to 2 and then to sigma of 2. And 2 gets sent to 1 and then to sigma of 1. So the 1 and 2 get swapped before you apply sigma to them. All the other values just get sent through to sigma. Anyway, it's pretty easy to see that this map is well defined, because if sigma was green, so sigma 1 was bigger than sigma 2, and you swap them, then sigma 1 will be smaller than sigma 2. Conversely, we have a map. I'm just going to copy paste it because it's basically the same thing. It's the same map, but from red to green instead of green to red. The maps F and G are mutually inverse, because swapping the first two values and then swapping them again gives you the original permutation back. So F is invertible, thus a bijection. Hence, the bijection principle yields, since you have a bijection from this set to this set, it yields that the sets have the same size. Ouch. Here. What's going on? This set has the same size as this set. In other words, the number of green permutations is the number of red permutations. Now, recall this equation. Now, what is this number? This is just n factorial, because we know how many permutations you have. So the right-hand side is the sum of two numbers, and as we've just seen, these two numbers are equal. So it becomes 2 times one of them. And therefore, this here is 1/2 times the number of all permutations. And as we know, this is the number of all permutations of n. This is n factorial by the preceding theorem. So you get 1/2 to n factorial, or n factorial half. That was one solution of the problem. This is an argument that's in a way called counting by symmetry. At least I call it this way, because we didn't count the green permutations directly. Instead, we defined another kind of permutations, the red ones, and we showed that there's equally many of them, so there is a symmetry between them in a way. And here is a second solution, which is more direct. So this is what we want to solve. How many permutations have sigma 1 bigger sigma 2? We can construct such a permutation sigma as follows. This is another of these dependent product arguments. First, we don't choose sigma 1 and sigma 2 separately. We choose the set sigma 1, sigma 2. This must be a 2-element subset of n, because these values must be different. So the number of choices is the number of 2-element subsets of n, which, as we know, is n choose 2 from the binomial coefficient section. So, having chosen this set, we immediately, so once the set has been chosen, the two values sigma 1 and sigma 2 are uniquely determined, because we want sigma 1 to be bigger than sigma 2. Normally, if we had just chosen the set, we would have two options of how to actually, which element would be sigma 1 and which would be sigma 2. But since we require that sigma 1 is bigger, we have only one option. Sigma 1 has to be the bigger element of the set and sigma 2 the smaller. Okay, now we have dealt with the first two values, and the rest we do as usually. So next we choose the value sigma 3. There are n-2 choices because it has to be distinct from sigma 1 and sigma 2. Next, we choose the value sigma 4. There are n-3 choices because it has to be distinct from sigma 1, sigma 2, and sigma 3. And so on until all values have been chosen. Thus, by the dependent product rule, again, the total number of choices is n choose 2 dot n-2 dot n-3 dot and so on dot. The last one is n-n plus 1, which of course is 1. And this, as you can easily see, is n factorial over 2. Check this. So this is something that you can easily compute. And thus, again, we have found that the number of these permutations that satisfy sigma 1 bigger sigma 2 is n factorial over 2. There are several similar problems. For example, you can replace this by sigma 1 bigger sigma 2 bigger sigma 3, and you will get n factorial over 6 instead.